In this section, we're going to learn how to assign oxidation numbers to different compounds. But before we do, we need to define oxidation and reduction. Oxidation reduction reactions involve the transfer or apparent transfer of electrons. You cannot have one without the other. You can't have oxidation without reduction and vice versa. Oxidation is defined as a loss of electrons, whereas reduction is defined as gaining in electrons. So if something loses electrons, it's undergone oxidation. Something gains electrons, it's undergone reduction. Seems a little bit counterintuitive that reduction is actually gaining something, but we're gaining negatives. One way to remember this is Leo the lion goes grr. Losing electrons, oxidation. Gaining electrons is reduction. Another way we can remember oxidation and reduction is with oil rig. Oxidation is losing. Reduction is gaining. Again, remember we're talking about transfer of electrons. So oxidation is losing electrons, reduction is gaining electrons. For reactions that are not metal and non-metal or don't involve oxygen, we need a method for determining how electrons are transferred. Chemists assign a number to each element in a reaction called an oxidation state or oxidation number that allows them to determine the electron flow in each reaction. Even though they look like charges, oxidation states are not ion charges. Oxidation states are imaginary charges that are just a way of keeping track of electrons. Ion charges are real, and we can measure them in the lab. So here are our rules for assigning oxidation numbers or oxidation states, and the rules are listed in order of priority. Any element that is by itself and not combined with another element has an oxidation state of 0. Monatomic ions, those are ions that contain just one atom, have an oxidation state equal to their charge. So for example, sodium +1 has a +1 charge or oxidation state, and the chloride ion, Cl-1, has a -1 oxidation state. The sum of oxidation states of all the atoms in a compound is 0, and the sum of oxidation states of all the atoms in a polyatomic ion equals the charge on the ion. Group 1 metals have an oxidation state of +1 in all of their compounds. So, for example, sodium has a +1 in NaCl. Group 2 metals have an oxidation state of +2 in all of their compounds. So, for example, magnesium has a +2 in magnesium chloride. In their compounds, nonmetals have oxidation states according to the list below. Fluorine is a -1, hydrogen is a +1, oxygen is a -2, group 7 is -1, group 6 -2, and group 5 -3. These are very similar to what we've done before when calculating charges. But in this case, we have to remember the order of priorities. So let's do a couple of practice. Let's assign oxidation states to each element in the following. In Br2, bromine is not combined with any other element, so according to Rule 1, it has an oxidation state of 0. According to Rule 2, potassium ion, so we see that there's a plus charge, so it has a +1 oxidation state. For the lithium fluoride, I like to create a little table and do in each and total. We know that lithium has a +1 charge because it's in group 1, and we said one of the rules was metals in group 1 always have a +1 charge. Now if we're trying to find out what the fluorine is, one of our rules stated that the sum of oxidation states in a compound must equal to 0. If lithium has a +1, then the fluorine has to have a -1 in order to make it 0. So it's a -1 oxidation state. So lithium has a +1 and the fluorine has a -1. Let's look at carbon dioxide, CO2. We go each and total. We don't know carbon. It doesn't appear on any of our rules. But we do know oxygen. Oxygen is a -2. Since there are two oxygens, the total of all oxygens is a -4. Again, this is a compound, so the sum of all the oxidation states has to equal to 0. So if that's the case, then carbon has to be a +4. So the oxidation state of carbon is a +4, and the oxidation state of oxygen is a -2. Let's look at our sulfate, SO4 2-. We're going to do each in total. Now oxygen is a -2. There are 4 oxygens, so the total of all the oxygens -8. Rule 3b says that the sum of oxidation states in our polyatomic ion has to equal the ion charge. So oxygen's -8, so we have to ask ourselves, what would sulfur have to be in order to make the total charge, or the total oxidation, equal -2? And that means that sulfur would have to be a +6. We're going to do a few more. Let's do KMnO4. What happens if we have 3 things? So each in total. Potassium's in group 1, so it has a +1. The total is +1 since there's 1 of them. We don't know what manganese is, but we do know oxygen. Oxygen is a -2, and there are 4 of them. Adds up to be -8. Has to still add it to be 0 because it's a compound. There are no pluses or minuses. So that means that manganese would have to be a +7 in order to make the total, the number of the positives, equal the total number of negatives. Add it to be 0. Let's look at Na2Cr2O7, each total. Sodium's in group 1, and it has a +1. There are 2 sodiums, so the total of all the sodiums is +2. Oxygen is a -2. There are 7 of them, so it's -14. This is a compound, so they add up to be 0. So that means that the chromium has to be +12. So the +2 plus 12 will cancel with a -14. Now, since there are 2 chromiums and they total to be +12, that means that each chromium has to be a +6. So the oxidation state of sodium would be +1. The oxidation state of chromium would be +6. And the oxidation state of oxygen would be -2. We're going to look at FeS, iron sulfide. Now this doesn't fall into one of our normal rules. So what we're going to do is say we know that sulfur, based on its position in the periodic table, has a -2 since we don't have anything else to go by. Well, if they have to cancel out and add it to be 0, since we have no pluses or minuses left over, the iron has to be a +2. So iron would have a +2 oxidation state, and the sulfur would have a -2 oxidation state. Just like we've done before when trying to name this type of compound, we named it iron 2 sulfide, and that's how we got that. Let's look at our ClO2-, each total. Each oxygen is -2 because we know that. It's a -4 and has to add up to be a -1. So in order to be a -1, that means the chlorine has to be a +3 oxidation state. So the chlorine is +3, oxygen is -2.